Right, this video is about a topic called parametric equations. And parametric equations are another way that we can represent curves either in the plane or when you get to Calc 3, represent them in space. We're going to focus on representation in the plane right now. And the first thing we want to do is look at something that we should be familiar with that can kind of segue us into the idea of uh, parametric equations. And that would be a circle like we use in trig. So, we have the unit circle that helps us calculate the values of various trig functions or represent those. And we know that extends to an arbitrary size circle, such as this circle here of radius 4. And we know that as we, starting at this point, which would course, so this is a circle, radius 4, centered at the origin. And as I move along the circle, starting with this point on the x-axis, and that would correspond to an angle theta equals 0. As I move counterclockwise and increase theta, then my xy points correspond to trig values, where the x value is the radius 4 times the cosine of the angle theta, and the y value is the radius 4 times the sine of that angle theta. Now, what we're going to do is we're going to make a little change. And instead of theta, we're going to call that t. And as I change t, right, if I use two equations where x equals 4 cosine t and y equals 4 sine t, and if those are, for all values of t, going to be my x and y coordinates. So you tell me what t is, I'll tell you what the corresponding x and y coordinates are. As you change t, this point will move along this circular path. So as t increases from 0 to pi over 2, my dot will move along this circle until I get to here where t equals pi over 2. And then my x coordinate, 4 times cosine of pi over 2, that would be 0. My y coordinate, 4 sine pi over 2, that would be 4. And so this point would be the point 0, 4, as sure enough it is. And as we keep changing t, as we vary t, each time we change t, we have the equations 4 cosine t and 4 sine t to tell us what the xy points are. And that's what parametric equations basically are. They describe a path. Like, a good way to interpret them or to view them is parametric equations describe a path through the plane. Okay, so in this case, as we change t, the path through the plane, the x and y coordinates through the plane, trace out this circle of radius 4. In general, parametric equations have consist of two coupled equations, where we have the x coordinate has a function f of t, the y coordinate has a function g of t. So the standard two variable description that we're used to is y is a function of x. You pick x, we calculate what y is. But we know there's limitations on the sort of curves that we can represent that way, right? Our vertical line rule, right? We can't represent a curve like, for example, this one, a circle. Hey, it fails the vertical line rule. We can't represent that using this two variable format, explicitly using the two variable form. right? You can't represent that as a function of x. We can describe it implicitly using something like x squared plus y squared equals 16 in this case, right? So we can implicitly represent the curve, but we can't represent it functionally this way. What parametric equations give us is a way to represent, by using two equations, to represent a curve where the x and the y are both functions of this third parameter t. So that's going to be what we're talking about now. Let's look at an example. So we already kind of looked at an example with the circular path. Let's look at an example of a different kind of path. So my parametric equations, and remember, you need both pieces for a parametric curve. You need both the x and the y piece. So x is a function of t, y is a function of t, and I personally like to view these this way. Instead of saying f and g, I like to just say, hey, x equals x of t, y equals y of t, to just kind of, reinforce the idea that x and y are both functions of this other parameter t. All right, but a lot of books will use other functional notations. It doesn't really matter, right? Just be aware of the context and what your particular problem or book is doing. But let's go ahead and do it this way. X equals x of t, that is 2t. Y of t equals 1/2 t squared minus 4. And t varies between 0 and 8. And this piece is common. Okay, it is common to have a range on t. Okay, where we're describing a path, but where t is varying within some range. Okay, it would be unusual to have t running not minus the positive infinity, say. Sure, you could do that, but t usually we usually have it vary within a range, and so we can view that as describing a path of a point or particle or something like that moving through the plane. Okay, so we can view it as describing a path through the plane. So if this is x of t and y of t are given like so, then one thing that we could do is we can, for different values of t, we can calculate the corresponding x and y value and then the point that gives us. So for this particular, we start t equals 0, and let's say t equals 0. We plug in 0 for t in the x of t and y of t equations, and we would get the point 0 minus 4. Or we'd plug in t equals 1, and we get the point 2 negative 7/2, and so on all the way until we get up to 8. We get 16/28. Right, and so if we plot those points and then we draw our smooth curve connecting them, because t typically is, we view it as ranging on a continuum like time, right? So I find it to be a natural interpretation to kind of view t as time. So this time parameter varying within some range. It doesn't necessarily need to be that. It doesn't necessarily mean that, but I think it's a good natural way to interpret it to help understand what's going on. So as we vary t continuously from 0 to 8, it traces out this path here. So we've plotted the points that we calculated in red here, but the black curve is the path it traces. And notice that as we increase t from 0 to 8, The path this traces out has a direction to it, right? It moves in a particular direction. View it as you're drawing the curve. I put my point down here at -4 there, and as I increase t and I'm drawing my curve, I'm moving my pen in a direction. And the direction in which the parametric curve is generated as we increase that parameter is called the positive orientation of the curve. And we can indicate it like we do here with arrows to kind of show us this is, as we increase t, this is the way the curve goes. And if we jump all the way back to our first example, right, we had arrows on this because as we increase t, here we might say t goes from 0 to 2 pi. And as I increase t, I would move counterclockwise along the circle. So the positive orientation of that parametric curve would be moving counterclockwise along the circle in the direction of those arrows. So that's what we mean by positive orientation. We can indicate it by arrows on the curve. Now, while we're on this example here, we can talk about the idea of eliminating the parameter. Sometimes, not always, but sometimes it is possible to eliminate the parameter from a set of parametric equations to obtain a description of the curve in terms of x and y. So the path of this example, right, just kind of quick look something like this, right? That is the sort of thing that we could describe in this y equals f of x form. Well, what would that be? If I described it that way, what would that be? And the way that we do that is we simply using one or the other equation, we try and solve for t in terms of x or in terms of y, and then we plug that into the other equation. So in our example here, right, all this is an example, obviously. So in our example here, we have x equals 2t. So I could say, all right, well then t would be x over 2. And so wherever I see t in the expression for y, I'd replace it with x over 2. So this would be 1/2 times x squared over 4. And that works out to be x squared over 8 minus 4. Y equals x squared over 8 minus 4. So if I graph that, that curve is going to overlap the path that we traced out when we drew the parametrics. Okay, so that's the eliminating the parameter idea. I'm not a big fan of that. It's a good concept to know. I'm not a big fan of it because really the benefit of using parametrics is you're able to describe all of these awesome paths and curves in space that you just couldn't do with the y equals f of x form. But you know, if it's the type of path like so that you could describe this way, and you want to know how, what functional form does that correspond to, that's what eliminating the parameter is all about. Now let's look at another example, and we can see how eliminating the parameter even though we might not be able to put it into a y equals f of x form, we might be able to employ the same method to try and get an idea of what the curve would look like. Okay, and so if I were to do something here, like try and solve for t, I'm going to have x. I'm going to have t equals like inverse cosine of x over 4 divided by 2 pi, and then try and plug that back in for t. So I've got a sine of an inverse, and that's not helpful. So, um, let's look at another way. So very often, limiting the parameter might involve getting a little clever. And so the clever thing I'm going to do is I'm going to say x squared plus y squared. Okay. Well, x of t and y of t are always going to be these things. And so I'm going to do 4 cosine of 2 pi t squared. And then I'm going to do 4 sine y part of 2 pi t squared. Okay, so that gives me 16 cosine squared 2 pi t plus 16 sine squared of 2 pi t. Now I can factor out a 16 here, and I have a cosine squared 2 pi t plus a sine squared 2 pi t. So sine squared of something plus cosine squared of the same thing. This whole thing equals 1. And so I have x squared plus y squared equals 16. Okay, well, I can recognize that as a circle with radius, right? X squared plus y squared equals r squared. So r is going to be 4 with the center at the origin. Okay. We can confirm this by using our parametric equations there to generate some points and trace out what those would be. And so if I do that, I start with t. T ranges from 0 to 1. So I start with t equals 0. I get the 0.40. As I increase t to 1/8, I get 2 root 2, 2 root 2, 0.4 when t is 1/4, and so on until I end up back with 4, 0. If I plot those points and interpolate the path in between them, trace that out, you see that this, as t increases from 0 to 1, this is tracing out a circle centered at the origin of radius 4 in a counterclockwise direction. Okay, as expected from eliminating the parameter. One of the most important parametric equations that types of parametric paths that we have, one of the most fundamental and basic, is a line. So the equations, x equals x naught plus at, where x naught is a constant, a is a constant, y equals y naught plus bt, where b and y naught are constants, and t can range between negative or to positive infinity, or any part thereof. That traces out, when a is not equal to 0, that traces out a line with the slope b over a passing through the point x naught, 0 naught. And if a is equal to 0 and b is not equal to 0, then that describes a vertical line. All right, so a quick example of that: x of t is 2 plus 3t, y equals 1 plus t. So jumping back here, right, we have x naught at, so we have x naught is 2, a is 3, y naught is 1, b is 1. The slope is b over a. That would be the point, or the slope 1/3, and the point x naught y naught would be 2, 1. And so that says that we have a slope of a line slope of 1/3 passing through the point 2, 1. And indeed, if we trace out that parametric path, that is what it gives us. All right, we can flip that around and say, hey, let's get a point that let's describe a parametric curve passing through these 2 points, a 0.47 and 2 minus 3. And how do we go about doing it? Now we kind of see what the answer is there, but let's go back and do it from the beginning. So we want to do the line passing through the point 47 and 2 minus 3. And there's 2 ways we could do this. So I'm just going to like jot these down, right? So 2 minus 3, 4, 7, not to scale, but there's 2 paths here. We could start at 4, 7 and end. So we could go this way, or we could start at 2 minus 3 and end there. Okay, we're going to do start at 4, 7, end at 2 minus 3. All right, so the first thing that we want to do is we want to note what the our parametric equations are going to be. They're going to be x naught plus at. They're going to be y equals y naught plus b t, and the slope is going to be b over a, right? So that's going to be the slope of the line. So first thing that we're going to need to know is what is the slope of our line? All right, well, what is the slope of our line? How do we find the slope of the line? The old change in y over the change in x. So the slope here is going to be minus 3 minus 7 divided by 2 minus 4. So that gives us minus 10 over minus 2. So that's a slope of 5. Okay, slope of 5. Okay. One complication here. Okay. One complication here is, okay, we need b over a to equal 5. But we can either do that by making b and a both positive or both negative. We need our line to go this way. Okay, we need our line to go this way. So we need, and let's go ahead and pick our point. So we want t equals 0 to correspond to our starting point for 7. So we're looking at our equations here, t equals 0. So we need x naught and y naught to be 4, 7. So our x is going to be 4 plus at. Our y is going to be 7 plus bt. But we need, as t increases, we need x to decrease and y to decrease. So we're going to choose our b over a to be negative 5 over negative 1. So that we have 4 minus t and 7 minus 5t. And that's going to give us the parametric equations that we want. Okay. One other wrinkle here, if you're faced with a problem like this where you want the path to start here and end there, not just paths through that way, is we need to find the range for t. Okay. Well, t equals 0 corresponds to our starting point. Okay, so 0 is definitely in there. But we need to figure out what our ending point for t is. It ends at 2 minus 3. So 4 minus t equals 2. 7 minus 5t equals minus 3. And we would solve for our t in that case And 10 equals 5t. So each side gives us t equal 2. So that's good. If that doesn't happen, then that means that that point wouldn't be on our parametric path. So that checks out, and t equals 2. And that's going to give us a path that starts at 4, 7, ends at 2 minus 3. That is describing a line segment for us. There's lots of examples we can do with different parametric paths. I recommend looking up a cycloid. That's a kind of a classic example of a curve generated by a point on rolling wheels. So that's a neat example. But let's do a calculus topic now. So we've got parametric curves. Now we want to talk about the how to calculate tangent lines. Okay, the slope of said tangent line. So suppose the black curve here, okay, the black curve is a parametric curve, arbitrary parametric curve described by x equals f of t, y equals g of t. And I want to find at the point t, I want to find the slope of the tangent line through there. Now, what I can do is I can pick a point a little bit of ways from t, and that's going to be the point where t plus delta t. And so that's going to give me a point elsewhere on the curve, f of t plus delta t, y equals g of t plus delta t. And I can calculate the slope of the secant line, the slope of the line passing through the point f of t, g of t, and f of t plus delta t, g of t plus delta t here. That slope of that secant line is simply delta y over delta x. Right? That's going to be the slope of this secant line. Well, if we look at that, so if we look at our curve here, we're going to use, we know that the slope of that secant line is delta y over delta x. And we can use the notion of the linear approximation that you would have touched on in Calc 1 that says that the derivative g prime of t times delta t is approximately equal to delta y. And delta x is approximately equal to f prime of t. You can also look at it another way. Let me just to kind of help remember it. So let me jump to here. Right. So we have x equals f of t. And if I want to find the derivative of x, okay, dx by dt, okay, that's f prime of t. But I can approximate that for small values by saying that is the instantaneous change with respect to t. The approximate delta x delta t, right, for small values is approximately f prime of t. And so that's another way to view where that linear approximation comes from. Okay, same idea for y is g of t, right? dy dt, that's g prime of t. But if I want to approximate g prime of t, well, that's for small values, delta y now over delta t. And so G prime of t times delta t is approximately equal to the change in y. Okay, so that's the linear approximation notion. So we can use that here to say that delta y and delta x are approximately g prime of t delta t, f prime of t delta t, respectively. And so the slope that we're looking for, okay, the slope of the tangent line, we can get that slope as we move our point, our secant point, closer and closer to our starting point, right? So as delta t gets smaller and smaller, we're getting the secant slope, delta y over delta x, gets closer and closer to the slope of the tangent line. So we can write that dy dx is the limit as delta x goes to 0 of delta y over delta x, right? That's familiar from Calc 1. But, and that just means, so here's our picture, right? So this is the secant slope. As we're moving this point closer and closer, right? I'm making delta x go to 0. Okay. But delta y is approximately g prime of t over, or delta t divided by f prime of t delta t, right? So as delta x goes to 0, that's equivalent to delta t going to 0. Okay, but we note that delta t is going to 0, but is not equal to 0. And so we can cancel these. And so the limit we get is g prime of t over f prime of t. And so that is our derivative. So the dy dx is g prime of t over f prime of t, or if you prefer, we can write that as dy dt over dx dt. And that's our derivative for parametric curves. So I have x equals f of t, y equals g of t. The assumption, of course, is that f and g are both differentiable on an interval for t. Then the slope of the line tangent to the curve at the point corresponding to t is dy dx, that's dy dt over dx dt, or using the notation that we had, all right, g prime of t over f prime of t. And that, of course, is provided that f prime of t is not equal to 0. Okay, so we could do an example here. Suppose I have the parametric curve x equals t, y equals 2 root t. Okay, and I want to find the derivative at the point. Well, just to kind of visualize it here, we see that, right, the derivative, let's go ahead and calculate that. All right, so calculate dy dx. Okay, y is 2t to the 1/2, right? So that's going to be 1/2 times 2, so that's just t to the negative 1/2. And dx dt is just 1, so that works out to be 1 over the square root of t. That's going to be our derivative. Okay, so different values of t correspond to different slopes of the tangent line, as you would expect. So if I jump over to my graph here, right, when t equals 0, well, the derivative is undefined. That makes sense, though, because we can visually see the tangent line at that point is vertical. All right, vertical tangent line, undefined. All right, so that makes some sense. Moving along, t equals 1. Again, we plug in t, and if t equals 1, so 1 over the square root of 1 is 1. So our tangent line there is 1, and t equals 4. But let's do t equal to 4 with a little wrinkle. Instead of saying t equals 4, what's the slope? What if I ask for the slope at the point 4, 4? Okay, and I phrase the question that, so I say I want the slope at the point 4, 4. Well, how do I answer that? Okay, well, the way I answer that is I need to find the t that goes with the point 4, 4. Okay, well, x equals t, y equals 2 root t all the time, right? So I'm saying I want my x value to be 4, so I need to find the t that makes that happen. I want my y value to be 4, so I need to find a t that makes that happen. And a quick word of warning. All right, so obviously in this case, I get t equal to 4. I plug in t equal to 4 down here. That checks out also. Square root of 4 is 2. 2 times 2 is 4. All right, so t equals 4, what works for both. And then I take t equal to 4 and I plug it back in there to get the corresponding slope. But let's say I ask for, okay, what's the slope at the point 4, 5? Well, I would do the same thing, except now I have the y value equal to 5, and I'm going to solve this, and I'm going to get 2 different t's. That means this point not on the curve, and so finding the tangent line at that point would be nonsensical. Okay, so just note that it needs, if you're being asked to find the slope or the equation of a tangent line at that point, then that point needs to be on the curve. And the t that satisfies your x of t and your y of t will be the same t, or that point's not on your curve. Okay. All right, let's add one more wrinkle to this just to kind of see the problem. So instead of the slope at 4, 4, suppose I ask for the equation of the tangent at that point. Okay. Well, all right, we've done our stuff. We've found t equals 4, and so I need the slope at t equals 4, and so it's the equation of the tangent at 4, 4. So the slope that corresponds with that is 1/2. Okay, great. But slope is only one part of the tangent line. Use the point slope form if you're looking for the equation. Okay, so y minus y naught, that's 4, equals the slope 1/2, x minus x naught, also 4, and then solve for y. Okay, so in this case, I get y equals 1/2 x plus 2, and that's the equation of the tangent line to the parametric curve x equals t, y equals 2 root t at the point 4, 4. Okay. Or when t equals 4, equivalent question. All right, the final topic with parametric equations is the length of the path, or the length of the curve. And so we have a curve C represented by the parametric equations x equals f of t, y equals g of t, and t goes from A to B. And we want to know what is the length of that curve C. Okay. This is the arc length problem. Okay. It's one of those fundamental calc problems. And how are we going to tackle it? Well, what we're going to do is we're going to chop up AB. Okay. Chop up this AV B interval for T into a partition, is what we technically call it. And that's going to be at one end A, so that's say T naught, that's less than T1, less than T2, blah, 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 blah. We're going to chop it up into, say, N pieces. Okay. And we're going to evaluate that curve at each of those pieces of the interval. So I'm going to look at, right, the XY coordinates, and that's going to be f of A, g of A, then f of T1, g of T1, and so on until I get to the f of B, g of B. Okay, so I'm going to look at all of those points, and that's going to give me something like this. Okay, so this is, again, just an arbitrary path, not saying that it has to be this particular path. It's just an arbitrary parametric path. We chop up the T range into pieces, and then we plot the, we evaluate parametric curve at each of those endpoints, and that's going to give us something like this. And then what I want to do is I want to look at one of those subintervals, one of those pieces of the curve. Let's call that the kth piece. And that's going to be from f of tk minus 1. So we're tk minus 1 to tk. So the 1 point on the curve is f of tk minus 1, g of tk minus 1. The other endpoint is f of tk, g of tk. I'm going to blow that up, and I'm going to look at that little piece in more detail. And see that little piece, if I want to, because it's nice and small, and I want to approximate that, I can approximate this arc length by this linear length here, by the secant line that connects f of tk minus 1 and g of tk minus 1 to f of tk, g of tk. And from the Pythagorean theorem, that's the square root of the horizontal distance, delta xk, plus the vertical distance, delta yk, both squared. So the square root of delta x squared plus delta yk squared. Okay. And that's approximately equal to that, the length of that little piece of my curve. So going back to our board here, the arc length that we're interested in is approximately, not exactly, but approximately equal to adding up the n pieces delta xk squared plus delta yk squared. Okay. But remember, with the derivative that we were just looking at, delta xk is approximately equal to f of tk delta t, square that, or sorry, f prime of tk delta t, and delta yk squared is going to be g prime of tk delta t, quantity squared. Okay, so there's a delta t squared for both of these that I can factor out, take the square root of, and put that on the outside. So then I am adding up the square root of f prime of tk squared plus g prime of tk quantity squared. Take the square root on the outside. We took the square root, there's single delta t. Okay. And so the length is about equal to that. But now, if I take the number of subintervals to infinity in such a way that it drives the width to 0, then this in the limit turns into, all right, so the length will be the limit as delta t goes to 0, okay, which is going to drive n to infinity in this sum. F prime of tk squared g prime of tk squared dt. And in the limit, that becomes an integral, okay, from t equals a to t equals b, square root of f prime of t squared plus g prime of t squared dt, and that is the actual length of the curve. And so that is our arc length formula. Okay, it's one of the fundamental calc problems. You will see it again in other contexts with polar curves, with other things. But the idea is the same as this. I'm going to chop that path up into pieces. I'm going to look at a little piece, do an approximation on that little piece, and then take the limit in a way that makes the approximation become exact, and that's going to give me an integral, and that's where the formulas are always going to come from. And so we can finish up with an example. For this example, we'll look at a type of curve called an asteroid. Okay, so this is a curve that looks like so. And so we have the parametric path, x equals cosine cubed t, y equals sine cubed t, where t goes from 0 to 2 pi. And we want to know the length of this path. Now, a word of warning on this. So, well, first let's do this real quick, and then we'll talk a little bit. The first thing is let's find the arc length. So the arc length, so in order to do that, I'm going to need to know x prime, and I'm going to need to know y prime. So x prime here is going to be 3 cos squared t, chain rule, right, times negative sine t, and then the y prime is going to be 3 sine squared t. Derivative of sine is cosine, so that's times cosine t. All right, so now the arc length then will be the integral from 0 to 2 pi, and we'll take the square root of the x prime part squared, so that's going to be 9 cosine to the 4th t sine squared t, plus the y prime t squared, that's going to be 9 sine to the 4th t cosine squared t. I take the square root of that dt, and that's the integral I have to solve. So my word of warning is this: very often these integrals are exceptionally ugly. Okay, and the trick for a lot of the paths that you're going to do is going to be trig identities. Okay, your friends, trig identities. All right, so in this particular case, right, we can do some simplification of terms. We can factor out, for example, here, we can note that there is a cosine squared and a sine squared and a 9 in all of these. And so square root, we can factor out a 9 cosine squared t sine squared t, and then we're left with a cosine squared t plus sine squared t. Okay, and then this is 1, and then this is a perfect square, and so it simplifies it a great deal, but not always. So just trig functions for a lot of these are going to be your friends. So that's 1, and you end up with 3 cosine t sine t. That should be doable by u substitution or whatever trick you like the most. So I'll leave that. I'll leave that to you. But just my word of warning: trig identities are often your friend here. And that is it for an intro to parametric equations. Hope that it was helpful.